Now we will discuss the next section, which is the registers. This is a simpler, is a simple section, not that much tough, but important. Okay. So registers. Before we go to this register, I will just explain why we need all these things. Because without that, you may not be able to understand it fully. So let's consider a letter A. This is a rough kind of explanation, or what we say, that some sort of introduction, or a kind of explanation, but that is not the whole story, or that is not the exact story. Uh, so I'm just explaining these things to in order to understand the concept. Okay, so this is not the exact processes and all those things. We have some more complicated things, but we just for understanding purpose, I'm just saying these things. So don't take it as a exact operation that is happening in the real life. So this is the let's consider as letter A. Okay, and assume this letter is expressed in binary format as 10111. As I said, this is not the binary format corresponding to letter A, it is something else. Okay, so this is not the exact binary code. So I'm just giving an example. So if you consider this letter A and assume that this is the binary code as corresponding to this particular letter A. Okay, so I hope you all coming from this computer science background. So if you consider this case, what this means, when you are entering your keyboard from your keyboard, for example, we'll draw a keyboard here. You are having a letter somewhere here, letter A. So many other keys also there. Okay. So when you are entering this particular letter A, what it means? The keyboard will send this particular code to your CPU. Okay. So because the computer will not, or your mobile phone will not understand letter A. It will understand only binary code. Okay, because it will understand only the machine language. So when you are pressing A, so this particular information will be sent to correspondingly. For example, if you are operating in Word, then it will be sent to the. So I will just give you a path diagram for that. So this keyboard is connected to your CPU. For example, I'm just drawing that block diagram. Okay, not the complete. So this is your CPU, and then from the CPU we'll be having the connection to your monitor, like this. So this connected to this monitor. So when you are pressing letter A, this same operation will happen in your mobile phone also. So I'm just so when you are pressing here, immediately a signal will send to this CPU. Okay. What signal it is going to send? It is going to send this particular code 10111. And in this CPU, there are some setup that will study in this module itself with that microprocessor and how it is dealing with this kind of instruction, all those things. So this inside this CPU, there are many operations with the ALU registers and all those things, and we have different address locations, all those things. So when you are pressing this A, this signal is going to send to this CPU. And suppose suppose you are working here in a Word file, okay, and you are typing something, and you need this letter A. So you just press that letter A. So signal sent to this CPU, okay, and that signal is not the letter A, but it is 1011. And if you suppose if you are pressing B, then it will be something like 110, some different code. This is not the exact one. So something will be different. Some binary number that will be different. So here let us say 10111, that is going to this CPU, and CPU will send corresponding signal to your monitor by with the help of arithmetic and logic unit and all those things. So it will understand this is coming from the keyboard. Okay, so along with this code, there will be additional codes which recognize it is coming from keyboard, and this code will be sent to CPU, and that CPU will understand this 1011 has reached here. Okay, and the CPU will understand what you have pressed in the keyboard, and the CPU will send signal to this monitor to blink some particular LEDs or LCDs in that monitor, which will show you something like this. Okay. Okay. At the same time, the CPU will also store the data, this data. Whatever you have written, that's 1011 will be stored in this in its memory. Okay. So basically, it will use this kind of data to do all these kind of processes. We will discuss more detail about the operation when we discuss the microprocessor. Okay. So this is the code that you have pressed in your keyboard. You have pressed A, letter A. Correspondingly, you have sent this particular code 10111 to the CPU, and CPU recognize you are in the operation in Word, in writing something in Word. Okay, so that will send corresponding information to this monitor with blinking of some certain LEDs or LCDs in your display as shown in here. Yeah. So that you will be knowing that you are pressed A. You pressed A, and it is shown in your monitor. And if you press something backspace and all those things, then it will be gone. So why it is staying there? Because the CPU also store that particular code 10111 temporarily. Okay, and you will be having that particular text in your monitor, and you will be writing all the other documents, paragraph, all those things like this. Okay. So you are having 1011. Okay, but as I said, 1011 is a binary code. Okay, and if you want to store this, we have different kind of memory devices. One of such device is called as flip-flop. One of such devices is flip-flop. So in a flip-flop, you can store one bit of information. So if you are having one flip-flop, then you can store one bit. So what does that means? So if you are having a flip-flop like this, for example, a JK flip-flop, you can consider JK itself, or a D flip-flop, you can see a D flip-flop. So in this case, you are having Qn here. You will be having Qn bar here. Okay. And after some operation, we will be having a state Qn equal to 1 and Qn bar equal to 0, for example. So you are having Qn equal to 1 now. Okay. And if you are having n number of such flip-flops, for example, for this letter A, how many we need? For this letter A, we need one flip-flop will store one bit. So this letter A is having 5 binaries bits. That is the binary value 1 or 0. So you need at least you need 5 flip-flops like this. So here we are having 1. Here we are having Qn which is equal to 1. Here again you are having Qn is equal to 1. Here we are having Qn equal to 0. Here we are having Qn equal to 1 again. Okay. So you are having number of flip-flops arranged like this. And by using this flip-flop, you can store this value A temporarily. Okay. So what that means? So 10111, which is stored in these flip-flops, D flip-flops or JK or SR, you can consider flip-flop D. So here we are having inputs like this. Connections will be there in your memory or in your registers. Okay. Okay. And this kind of flip-flops, or we can say, if you want to increase the number of bits that has to be stored. So as I said, in one flip-flop, you can store only 1 bit of information. 1 bit you can store in one flip-flop. And if you arrange a group of such flip-flops, then you can store number of bits. Okay. So if you want to store this A, if you're writing something in by using your computer, and if you are pressing A, you are having this 1011 sent to CPU, and CPU will send 1011 to your memory location, that is into these flip flops. Okay. And that will give, for example, this CPU will be sending 1 to this one and 0 to this one. Sorry, this one also 1, this one also 1, this one also, this one is 0, this one is 1. So CPU send all those values into these flip-flops. Why it has to send? Because you need that values as long as you are working in that particular program or in that particular process, whatever you are doing. So if you are writing something, it has to show letter A in your screen as long as you close that window or you delete that particular sentence or letter. Okay. So until that, it has to store, the CPU has to store those particular values somewhere, and that will be stored in these flip-flops. And if you arrange number of flip-flops like this, then you can store a large number of bit of data. Okay. Suppose if you want to write something like hi, okay, or something like good morning. So consider this as your, as an example, A is having this much of code. A is having much more larger binary value, not this one. So if you are considering this particular code as your A, and if you consider this kind of a word or words, if you consider, then we need more number of binary values, right? For G, we will be having some code 0 1 0 1 1 1, and O, we are having some other code 1 1 0. Okay. So we need more number of binary values or digits, bits we have to store in this memory. So we need large number of flip-flops. We need large number of flip-flops arranged like this. And if you are having a large number of flip-flops arranged like this, or a group of flip-flops, then such kind of arrangement, which is called as register. This is called as registers. So basically, in a single flip-flop, you can use only 1 bit. You can store only 1 bit of data. If you are having n number of flip-flop, then we can use we can store many data at the same time. Okay. And if you are using such kind of a configuration, a group of flip-flops, then it is called as a register. So register basically we use to store this data. You can write the notes simultaneously. So the flip-flop is a 1-bit memory device or memory cell, you can say. And if you are having, in order to increase the capacity, we have to use a group of flip-flops. Okay, so such a group of flip-flops are known as registers. So I hope you understood this particular example. I will explain this in more detail when we discuss the microprocessor and the CCD, all those things. Okay. So now we will go to the registers. So we already discussed registers are a collection of flip-flops or group of flip-flops that we use to store the data, binary digits. Okay. So, so we can consider it like uh, but I'm not going to write all those things because it will take much time. Okay. So if you consider a flip-flop, which will be using to store a 1-bit data, or we can say which is a 1-bit memory cell or memory device, memory cell. And if you consider registers, which is nothing but a group of flip-flops, which is called as registers. You can search for a definition. This is just some for understanding. So this is called as this we use to store more data. Okay, and then if you are having n-bit register, n-bit register, okay, which means that you can store n bits. So it will be having n number of flip-flops. So an n-bit register can store n bit of data, and which will be having n number of flip-flops. Okay. So as we discussed earlier, in the case of flip-flops, with each negative triggering, we are having change in your state. Okay. So if you consider these registers, you can consider it like this. If you are drawing it in a symbol form, you are considering a 4-bit register. You can consider it like this. So you'll be having input. Let's consider this as your D flip-flops. So then we will be having output through here, Q. So similarly, we will be having D inputs here, and Q, you are taking output from this side. Okay, and we'll be having that clock negative triggered. Okay. This is your clock. So as you know, in this kind of configuration, when your clock is changing, okay, when your clock is changing, your output is going to change. Output is also going to change. Your memory is going to change. That is not preferred, right? Because when you are operating in something by using your computer or mobile phone, you need that particular operation. for as long as you are continuing that operation, that particular process. So you do not need any change in your memory, right? So in order to avoid this kind of change of memory or toggling with the clock pulse, okay, we will connect load to this particular circuit. So we have another connection which is called as load. This can be synchronous load or asynchronous load. And also we have one more connection with this, which is the clear. Clear means if you are giving signal to this clear, then it will erase all the data which is in the memory. Suppose you are pressing your backspace in your screen, in your keyboard, okay, and you have already typed letter A, for example, in your uh, keyboard, and it is shown in your desktop. And if you do not want this particular letter, then you press that backspace, right? So when you press that backspace, this particular letter will be erased. How it is going? How it is doing? When you are pressing that backspace, CPU will send signal to this particular end, or this particular input, or input in this particular line of this register. That is nothing but your clear. So when you are having signal which is sent to this particular circuit or this particular connection or input, then it will clear entire data in this particular register if it is synchronously connected to all this, if it is connected to all these registers. Okay, so we are considering that this clear is connected to all these registers, and if you have any such kind of clearing option, it is required, and you press that backspace, for example, this is just an example, then it will send the CPU will send signal through this particular line of your register, and it will clear all the data inside. So we have these three different connections basically, apart from the flip-flop. One is clock, we already discussed. And when you are using the clock, you will be having a change in your state, change or the toggling that will happen in your output. So in order to, because you are continuously operating on that particular process, you do not require any change in your output, or the memory has to be the same. So we need this load, synchronous or asynchronous load, to make it stable. They are put in order to avoid that toggling effect when you are considering the memory, when you are storing the data. Okay, we are talking about storing the data. Similarly, we have another one which is clear, which is used to clear the all the data which is stored in this particular register. Okay, and for example, if you consider the synchronous case, if you want to change the data, then the clock has to be high and the load also has to be high. For asynchronous case, if you want to change the data, the load has to be high. The clock, it does not depend on clock. So that is not that much important. That's why I'm just skipping those things. Okay, so now we'll consider the classification of these registers. Classification classification of registers. There are different kind of classification basically. So based on what we are classifying, depending on that we have different kind of classification. So let's consider first classification depending on the input and output. Okay, so depending on input and output. So this way, by using this particular method, we can classify them as serial input, serial input, serial output, and this one is called as serial input, serial output. So then we can have serial input, parallel output, serial input, parallel output. Then I will write other things, other two I will write short form only. Okay. So the next one is parallel input, serial output. Then last one is parallel input, parallel output. So this way we can classify these registers based on their input and output, how we are providing input and output, how we are providing input and how we are taking output from the registers. Depending on that, we can classify them for serial input, serial output, serial input, parallel output, parallel input, serial output, parallel input, parallel. Okay. So what I mean by this is that if you are considering your register like this, suppose your register is like this. So now I will be drawing like this. You have to assume it as registers. This as register. Okay. So suppose you are providing your data inside, for example, some 1011 you are giving. Okay. So your D is here. So you are providing this data like this. So this is a serial input. Okay. This process is serial and serial input. And if you take the output from here, so it is going to be serial output. So once this one is entered into this particular flip-flop, then it will pass to this next flip-flop. It will after that operation of the first flip-flop, it will go to the second one, and then third one, then fourth one, and then comes out. After fifth one, it will come out. So this kind of operation, that you are providing the input data at the first flip-flop, and it is given its output to the next flip-flop, and next again, and continuing that process, and finally you are getting output after this last flip-flop. Then that kind of operation, which is called a serial input, serial output, because both of them are serial with respect to this register. Now, if you take your output from if you're considering, if you're taking your output from each of the flip-flop, once you're providing this input like this, and you're taking output from each of this flip-flop like this, okay, let's say this is the 5-bit data, then that means you are taking output from here. And that particular process, which is called as serial input and parallel output. So output is taken parallelly, but the input is given serial. So serial input, parallel output. So here parallel output is like this. You are taking from all the outputs, which means that this is Qn. You are taking from each of these flip-flops. Now, what will be the parallel input and serial output? It's just the opposite of this. So parallel input means you are providing input parallelly. So that I cannot show here. I will just show here like this. Okay. So you are giving input parallelly to this. So your input is here. All these are inputs. Okay. All these things. are inputs, and you are considering output from here. You are taking output from here, from the last flip flop. So you are providing input parallelly, taking output serially. So that is called as parallel input and serial output. This one, third one. If you provide all inputs parallel, and if you take, what that means, providing all inputs parallel means you are providing input to each and every flip-flop separately. You are not providing only on this first one and then going to the second, then going to third, not like that. We are just simultaneously giving flip-flops, these inputs to these individual flip-flops. All the flip-flops we are providing. So then it is like a parallel connection to individual flip-flops. So it is a parallel input. Okay, but you are taking your output from this last one, which means that it is serial. Output is taken serially. And if you are taking output like this, so here we are providing input parallelly, taking output also parallelly from each of those flip-flops, then it is called as parallel input, parallel output configuration. We will discuss all these configuration in detail anyway. So this is just a representation what this classification means. Another classification which is based on the application. So depending on application, there are many other classification also. So depending on application, we can classify these registers as two. One is the shift registers, and the second one is storage registers. Storage registers. So shift registers will use to shift the data, okay? And storage registers, as the name suggests, it will store the data. This will be using to shift the data, which means that from one location to other location, it has to pass the data. Then we have to use shift registers. And for this storage, we use another kind of registers, which is storage register. This is nothing but this PIPO, parallel input, parallel output, can be used as a storage register. As a storage register. We will discuss how it is going to work. Now, first we will discuss the serial input, serial output configuration. Okay. So, this we will be considering in case of shift registers. Shift registers. So, in this shift registers, we will consider serial input, serial output. So, we will considering, first we will consider serial input, serial output. So we are talking about shift registers now, and we will discuss all the four categories within this shift registers. So we need, for example, we consider a 4-bit register, which means that we are having 4 flip-flops. So just go here. We require 4 flip-flops. All of this should have the same size. So we can draw it in a much more better way. Okay. So this is my flip-flop 1, flip flop 2, flip flop 3, flip flop 4. Or you can take it as a reverse way. So because we are taking it as 3, 2, 1, and this one is 0. I'm just taking it as a data values. Okay. So this is flip flop 0, just denoting that. Okay. Or you can take 1, 2, 3, etc. Anyway, it is not a matter. So these are my flip flops. So we have the input here, and from this flip flop we are having the input to the next one, and from here we have the input like this. And we'll be having the clock provided to each of these flip flops. So this is my clock, and as you know, this is negatively triggered. Okay. Now this is your input D in. Now we'll be having different values. So this is my D0, this is my D1, this is D2, and this is D3, and this is Q3, Q2, Q1, Q0. These are the output. These Qs are the output. And here we are considering this CISO, that is serial input, serial output. This is in right shift mode. This is also another classification. This is right shift mode, or we can say shift right mode. Shift right. Okay, because we are shifting from left to right. Similarly, we can also do the same with which can shift from right to left. Both way you can do. So this one is shift right mode. Shift right mode means we are shifting towards the right. Okay, so this is the circuit for CISO, serial input, serial output. So we are taking output serially from here at the end of this flip-flop 0. So this is our final output. We'll take from here output. Okay. So now what will happen? This kind of, for example, we are considering 4-bit data. Let's consider some 1101 case as our input. Okay. Suppose you are we just pressed letter A, and letter A is 1101. So that information is passed from keyboard to the CPU, and the CPU will store it somewhere, or the data will be shifted from some place to another place if you are considering. Okay, because you are considering shift register here. Okay. So, and if you want to pass that particular information 1101 from one location to the other location, so that will be reached at this particular input terminal D in. Okay. So first this one will enter. So this one will be entering. So it will be. So this D3 will become 1 now. D3 is now, this one will be 1. Okay. So in that case, your Q3 is also will become 1 because when you are considering that D flip flop, as we discussed for D flip flop, it will be just following this particular input D. You can go back and check for D flip flop, whatever input you are given, that will be coming as your output. Okay. So when you are having your input which is equal to 1 here, then your Q3 also will become 1. But at this time, D2 is 0, D2 is 0, Q2 is also 0, D1 is 0, this one is also 0, this 2 also 0. So initially when there is no data, you are having this is 0, this is 0. All of them are 0 initially. Then when you are having that first clock pulse edge comes, that is negative triggering, which is coming. So in that time, this state is going to change. So in this case, so you are having this data, which is 1 here and 1 here. And with the next clock pulse, that is the next triggering, then we will be having this particular output Q3, which will be fetched into this D2. Okay, so this 0 will become 1, and here it will become 0 because your input now it is 0, and here also this will become 1. This is again 0, 0, 0, 0. So basically that initial values are shifted. So I will write both of them, and only we can understand that. So initially all are 0. Then we have here 1. This is also 1. This is 0, 0, 0, 0, 0, 0. So the output is now 0. Output is 0. Now for the next clock pulse, when the next clock pulse arrives, this one shift to this particular flip flop because you are connected this Q3. So in that time, this will become 0 because the input is now the next data, that is 0. So 0, 0 comes here. Here it will become 1, 1. Then here it is again 0, 0. This 0, 0 shift here. This 0, 0 shift here. Okay. Next time this 1 will be given to this D in. So this will become 1. This again also will become 1. This Q2 value 1 will be fetched into the next flip flop if you want. So this 2 will become 1, and this 0, 0 will be shifted to this particular flip flop. So this will become 0, 0, and here it will be again 0, 0. And when this one is given or fetched into this D in input, then again this one will be 1, 1. This one will be shifted, that is Q3 value will be shifted to the next one. So this will become 1, 1, and this one will become 0, 0. This again will become 1. Now all your data, that is input binary values are fetched into the register. Okay, so we are having the output like uh, the output now is like first you got 0, then 0, then 0, then 1. But that is not the signal that you have given here. Here given 1101. So now we need more pulses. More clock pulse has to be given to this particular register. Then only it will shift further. Okay. So I will just erase that. I will just erase this to write it on top of those. So what will happen to the next clock pulse? I mean fifth one. So in that case, it will be this one will be shifted now. So this will become 0 0. This will become 1 1. Sorry, this also will become 1 1. 1 1. So this state is changed to this one. So this is changed to the shifted to here. Again, this is again becomes 0 0 0. Then here it is 1 1. Then here it is also 1 1. Again 0 0 0 0. And here also it will be 0 0 1 1. And finally, oh, this much is enough. Okay, now you can see. Now if you look, there is a shift you can see. You can see a shift here as it progressed. For example, if you consider this 1 1, it is shifted to here, this 1 1, then it is shifted to here. Similarly, all those values, if you can check, you can see that it is shifting from first flip flop to the next one with the clock pulse. Okay, so now if you are checking your output for 4-bit output, if you are considering now, then you can see the output will be coming from here. You can see from here this direction 1011. So you have to consider it like this. You can see this is 101. Your output is 101. So this is how the serial in serial out shift register works. Okay. Similarly, you can also consider different values and check how it is coming at the output. So when your fourth pulse comes, you stored all those values here. You already stored all those values in these registers. As you can see in the fourth one, 1 2 3 4, you can see from here when you are at your fourth cycle of your pulse clock pulse itself, you have one here, then the next one here, 0, then 1. So this is stored in this particular register. Okay. So if you want to take that out, then you have to consider the other clock pulse also. But if you just want to fetch that data into this register, in that case, you need only 4 clock pulse in this particular case. Okay. So if you are considering only up to this case, okay, you are having values in Q1, Q2, Q3, Q4. Sorry, Q0, Q1, Q2, Q3. You are having values exactly as you have provided at the input. can see from here. This is 1, this 1, 0, and again 1. This is just stored, okay, but you cannot get that data. So if you want to get that data, again you have to shift. So from here onwards, you have to consider the output as your Q0 because you are taking that output serially. You are taking output serially, not parallelly. So you have to get the output serially. In order to get that, you have to apply more clock pulse and you have to do the same process, and then you will get 1 first, then 0, then 1 1 as your Q0 at the output. Okay, so this is how this particular CISO works, serial input, serial output works. Now we will check its pulse diagram as well as the states. So let's consider first clock. We can say this is a truth table or something. So this is the initial state, or initially we can say. And if you consider Q3, Q2, Q1, Q0, all these states are 0 initially. So these are the zeros. Okay. Now we are having, when you are having first negative triggering, at that time you will be having Q3 value. What is that? Q3, where it is coming? Q3 is this one. So first triggering, Q3 will become 1, right? So Q3 is going to become 1, all others are 0. Then in the next one, Q3 will become 0, then all others are, this one is 1, then this is are zeros. Then for the next pulse, this one will be 1, 0, 1, 0. Then for the next clock pulse, triggering, this one will be again 1, right? This is 1, this is 1, this is 0, this is 1. So basically you can see a right shift. You can see a right shift here. This one is shifting. This one is shifting with each of this clock pulse triggering. Get the trigger, it is shifting towards right. Similarly, all other values also you can see shifting with this clock pulse. Now your data is stored. Okay, within this fourth triggered, your data is stored as 1101. But this particular configuration, CISO, which means that serial input and serial output, we have a problem that we will not get output directly from this Q3, Q2, Q1, Q0 because we are taking the outputs serially. So we can take the output from Q0 only. Okay, but when you are considering that case, then we are having 4 zeros here. Only these 4 zeros we are having initially, then only this one. So that is not the output that we require, right? Because we are not giving the data which is 0 0 0 0 1. That is not the data that we have provided. So in order to get the data, we have to give more additional clock pulse. For example, like more clock pulse if you are giving here, then this again shift. So here we will get 0 as input, there is no input there. And this one will be shifted to here. And this one will be shifted to here. This 0 will be shifted to the last position. Okay. And the next clock pulse will be having this 0 will be shifted to the next position. So this will be 0. Again, here also 0. This one will be shifted again to this position. Then here we will be having this one which is shifted. And for the next clock pulse, we will be having 0 here again. This 0 shift to this next position, 0. Q2, and Q2, from the Q2 it will be shifted to Q1. This 0 will be shifted, this one will be shifted to this one. And now if you look, then we will be having this data, which is what you exactly required, 1101 in this one. Okay, so this is the serial input, serial output shift register, which is a right, which is in the right shift mode. Okay. Now, if you consider the clock pulse diagram of this one. So first we have to consider the clock pulse. So let's consider the clock pulse. So okay, I will just try to draw it here itself. Let's consider this. Okay, so this is the clock. And we are having that input D in. Okay, let's consider the D in as. So within one first clock pulse, we are having initially this D in also 0. And then the first triggering, we are having that which is equal to 1. So here we are having that 1. Once here it is 1. And in the next one, it is going to become 0, right? Consider it like something like this. I should have given you example with the whole 1 first. Then it will be much more better. Here it is 0. Then again it is going to become 1. And it is continuing 1 for the next pulses, right? So here the third one, fourth one, next one it is 0. And it is 0. So I'm considering values 1, 0, 1, 1. Okay. And remember that this is the least significant bit, as I said, LSB. This is the most significant bit. This is having less important. This is having most important. So this is most significant and this is least significant bit. So it will be going like this. First it will enter, first this one will enter, then 0, then 1, then this one. And we have to take the values like Q3, Q2, Q1, Q0 as we discussed. So we have to consider Q3, Q2, Q1 and Q0. Okay. So this high state means this is 1, this is 0, this is again 1. Again. So in the first state, we are having clock pulse. This is we are having 1. So at that time, Q3 is going to become 1 at this first stage. this. This time interval should be same. In my drawing, it may not be the same. Pulse duration should be same. Okay. So once it is, we are initially considering Q3 also 0, then it is going to become maximum. Okay. So in the first that's triggering, it is going to become 1. And Q2, what is Q2 at the first stage? It is 0. So in the first, I'm drawing on the basis of this. Okay. So this is the first negative triggering. So Q3 is maximum. So all others are 0. So all others are 0. So this is Q2 is 0 up to first triggering. 1 is 0 in first triggering also. Q1 is also 0. 1 is also 0. Q0 is also 0. Then in the next one, next triggering, negative triggering, we are having this one is going to become 0. Okay. And this one is become 1 because this one is shifted to this second flip-flop D2, and D2 since D2 is equal to 1 now, Q2 also will become 1 because D flip-flop will give you output same as your input. So now this Q2 is maximum, but all other values are zeros. These are zeros. And the next case, this will be going to become maximum because the next one will end up into D3, and that will give you Q3 is equal to 1. And this one, at that time, this one will be 0. And this value 1 should be shifted to Q1. So Q1 will be maximum or high. But Q4 is still 0, right? Yes. Now for the next pulse, again shifting will happen. So the next one will come here. So this one is again 1, and this one is shifted. So this one is also become 1. This one is going to become 0, and this one is going to become 1. So now you can see from that within that fourth, where is that? I don't know. Okay, so we can see within that this triggering fourth one, we have all the data which is stored in the flip-flops. You can see that. You can see from here data which is stored in this flip-flop 1101. Okay, which is already entered into that. How we can see that in this diagram, so that we can observe from this diagram. You can see here it is. Here it is 1. Here it is again 1. This is 0. This is 1. So 1011. That is stored after this fourth triggering or fourth clockwise. Okay, so this is how it's coming. Now, if you further draw, continuously draw this. I'll show you. So now your Q0 is 1. You got this 1 as your output, and this will be shifted continuously as the clock pulse goes. So we can have continuous variation. Let's say this is the next 3 edges. So I'll just draw this one also. And this one will become 0 because there is no input after this fourth bit, and this one remains in 1 as such. This one will become high, and this one will become low. Again, this is again 0, and this will be 0 again, 0. This will be remaining in high value. This one is going to become high. So the next one, maybe one more. So in the next figure, so this one, so this here it will be 0. This one also will be 0, and this one also will be 0. This is going to 0. This will be remaining in 1. So now you can see the same scenario. We have got the output. We got the output. We got the output. This is 1 now. This is 0. This is 1, and this is 1. This is what we require, 1 0 1 1. So if we are considering that in this fashion, then it is 1 1 0 1. That is the output that you have. You can get through this Q0 because we are taking the output sequentially or serially. Okay, we are taking the output serially. So because of that, we have to consider the output through Q0, and the output will be given like this after shifting. Okay, so in serial input, serial output, we need more clock pulses to get the output. Complete data through this shift register. But if you want only storing, then you need only these 4 clock pulses. Okay, so I hope you understood this. And we will be discussing the next flip-flops, next registers, shifting. Very briefly. So we will not be considering these kind of diagrams and all those things in that case. You can do it by yourself. So, okay, I will erase this. So next one is let's consider serial input parallel output. Serial input parallel output configuration. So here also let's consider 4-bit case. 4-bit register. So which means that we need 4 flip-flops. 4 flip-flops we need. Okay, so here this is the input. So we are talking about serial input, parallel output. The serial input means the output of the first flip-flop will be fetched into the input of the second one. Okay, remember that. And here output of the second one fetched into third and like that. So that is the serial input configuration. Output of first flip-flop will be fetched into the input of the second when you are having that serial input configuration. We can denote these things. This is your D3, Q3, D2, Q2, D1, Q1, D0, Q0. Okay, and you are having that out pulse here. Oh, you don't need this. So serial in, okay, serial in and parallel out. Parallel out, we have to take the output parallel. So we need an additional connection from each of these output. Q3 from Q2 and Q1 then Q0. Now the same scenario will happen. Okay, let's consider the same number 1101. Okay, and we have to give that particular binary value 1101. So 1 will be entering to this D3 first, then 0, then 11. Okay, so this is a serial in. Okay, so it also require 4 clock pulses to completely store this data. Completely store this data. This configuration also require 4 clock pulses. But the advantage of this particular configuration is that this we need only 4 clock pulse in order to take the data out also. Okay, we only need 4 clock pulses. So for example, once you have completed all those 4 clock pulses, so it will be like the same scenario that we discussed earlier for the case of serial in, serial out. It will show here. Okay. The same scenario here. I don't know where to say. Okay, so here we can see when it is reaching at this fourth trigger, okay, when it is reaching at the fourth inverted clock pulse or the edge, we can have negative edge. We can have this kind of data in Q3, Q2, Q1, Q0. This is same because we are using serial in. The serial input we are considering. So we require these first four clock pulses to store the data first. So 1101 will be stored in Q3, Q2, Q1, Q0 for the case of serial input and parallel output case. So that is same. Okay, but it does not require these clock pulses to take the data out, because here we are having this particular Q0. We have to consider output through this Q0. So, but in this particular case, we do not require but we are not only depending on this Q0, but we are considering all these Q1, Q2, Q3, all those outputs also. Okay, so in that case, we need only 4 clock pulse. Within that 4 clock pulse itself, we will get all the outputs. So we can see once this value which is stored after the fourth clock pulse. So after that fourth clock pulse, after that fourth negative triggering, so we'll be having the values like Q3. Q3 will be having value 1. Q2 will be having 1. Q1 will be having value 0. And Q0 will be having value 1. And in the case of serial input, serial output, we have to apply more time pulses, okay, or clock pulses to this particular resistor in order to get the output through this Q0, because we have only this way we can take the output, because we are considering serial output. Okay, so but in this case we are taking the output parallelly, so we can get the output from this particular configuration itself, because we are considering taking output parallelly through here. So we are having 1 here, Q2 we are having 1 here, Q1 we are taking parallelly, so we are having 0 here, Q0 also we are taking here, so this one. So we'll get the value, binary value that we are given through the input. We can get the output parallelly within the fourth clock pulse. Okay, that is the advantage of this serial input parallel output configuration as compared to serial in parallel out configuration. Okay, so we require only 4 clock pulses. Within that 4 clock pulses, we will get the output also. Both input we can store as well as we can take the output also within that fourth clock pulse. And when you consider the case, let's consider parallel input and serial output, or we can consider parallel input and parallel output, parallel input and parallel output. So parallel input, parallel output, how it will be coming? I think I can, let me see whether I can draw it here itself. Okay, so maybe you can write it. Okay, anyway, I will draw it here. So parallel input, parallel output. So we are providing the input data parallelly. Also, we are taking the output also. Output, we are taking output also parallel. So let's consider it like this. Okay. We have this now we are providing input also parallel. Okay, so we are providing input parallelly. So For individual flip-flop, we are providing input separately. So in this parallel input configuration, we are providing input separately to each and every flip-flop. Okay, so this is your D3, D2, D1, and D0. And you are having Q2, Q3, Q1, Q0 as your output. And you also have that clock pulse into having this clock. So this flip-flop will be active only when the clock is at low or clock is at 0. Remember that. Again for this one. So you can see this is your clock. Let's just erase the remaining part. So here we are providing the input data parallelly. So here we will be having directly you can give 1, 0, 1, 1 data here, and directly you can take data parallelly. So you'll be taking data like this. You can draw it neatly. So you can directly take data as your output of each and every flip-flop like 1, 1, 0, 1. So this is the parallel input, parallel output configuration. And as I discussed earlier, parallel input, parallel output configuration will be also used as a storage register, storage register. Okay, or we can also call it as buffer register. Why it can be used as a storage register? Because in here we are providing the data through parallelly to this shift register, and also we can take the data parallelly. So the data will be there as such, as you can see from this figure. So it is just like as storing the data. Okay. So and now the last configuration. So here you are not changing any output of any flip flop. Okay, Q1, Q2, Q3, Q0, which are as such. So there is no change happening in this outputs. So this can be act as a storage register. Can be acting as a storage register. So values are not changing here. And we have the last configuration, which is the parallel input serial output, that you can do by yourself as a homework, but it is a little circuit is not that much easy for this one. I'll just show that first. But it is not much difficult. If you understand, then it is okay. Third one. Let's go that first one here. Okay, here we have some more connections, some more diagram Let's consider that this NOT gate here, which will be connected. And one connection which is before this NOT gate. Okay, so here we have the input, which is directly B1 here. Let's say this is your B1, and then you have this output, which is given to a AND gate. So this has to be given to a AND gate. Okay, and connection from here also given to this AND gate, and one more AND gate is there. And we have the bit connection first, and then we have this one. This one connected. This diagram is easy, but having some more to draw as compared to the other configurations. You have to draw more connections and all those things. Okay, so that's the first one. And the second one, you have to take the output from here. Same thing, repeating. AND gate here. And the second leg of this AND gate is coming from here. And this we have another AND gate, which is bit connection. Then okay. And this is given to a OR gate. That is given to this input. This is simply an OR gate. Okay, OR gate. Again, we have the next one here. AND gate connection from the last one. And then we have this connected to the next AND gate. We have the fourth bit, and these two are connected to an OR gate again, and that is given to this input. Finally, so this was given as input. Okay, I think that is good. Now let's consider this as your B0. This is your B1. Okay. This line which is B2 and this B3. Bit 1, bit 0, bit 1, bit 2, bit 3. Okay. And you will be having this as your D0, D1, D2, and D3. Similarly, you have Q0, Q1, Q2, and Q3. You are taking output from this Q3. So here we are having parallel input and serial output. Parallel input and serial output. Okay. So in this case, we have a B0, B1, B2, B3. These are the bits, and you have to consider Q0. So here we have two different states or configuration or mode of operation. First, we have to load the data. So we have shift or load. These are the two modes of operation. So two modes of operation. One is shift mode, and the other one is load. Or first you can consider load because it is happening first. Load mode will be happening first, then shift happens. So first one is load mode. Circuit operation first will be load. Second one is shift mode. So in load operation, so I will use one bar here because we have to consider 0, 1, right? So when this is 0 means when this line is 0, which means that there is no shift. In other words, it is load is active. So that is why I am putting one bar here for the load, because when this line is 0, here we are providing 0, load is active, shift is 0. Shift is 0 means shift is not active now. So in that particular case, your values will be loaded. Why? Because this line is 1 now and this line is 0, right? Because it is inverted by using this NOT gate. Okay. So this one is 1. This one is 0. So this value here it is 1. This one is also 1. This one is also 1. But here it is 0. This is 0. This is 0. This is also 0. So in that case, this NAND gate will give you 0. This NAND gate is also giving 0. This NAND gate also will give you 0. And we are providing this B0 directly into D0. This B1 we are providing. So here it is B1. And here also it is B1. So B1 or 0. So here also we'll get B1. Similarly, B2 here. B2 comes here. B2 dot 1 will result B2. And B2 or 0, that is also giving you B2. B2 plus 0. So that is B2. So B2 will be also given to this B2. Similarly, here B3, we are having B3 here. So B3 comes here, B3 into 1, B3, B3 plus 0 or B3 or 0, that is again B3. So D3 is given this bit. So this can be, for example, something like one, let's consider some value, something, some binary code. Let's consider this as 1, this is equal to some 1, this is equal to some 1, and this is equal to 0, some values. Okay, so that values will be given to this AND gate, and that will be taken product with this 1, and that will be given B2, E2 taken OR with this 0, and that will be given B2. So that 1 will be coming here, B2 equal to 1 coming here. Okay, in this way we are parallelly giving input. Okay, so in this time this load is active because this line is 1. There is no shifting happening, but the input is loaded in this particular each of these flip-flops. Input is loaded. Then after that shifting is happening when you are having this line is this line becomes 1. Suppose instead of 0, when this line is 1, when this line is 1, then load is this line becomes 0. Load will become 0. This particular part is 0, and this one will become 1. So this is 1, this is 1, this is 1. Now your input is already loaded. B1, B2, B3, B0 all are loaded. Now this will become 1. So when this is 1, then this output Q0 will be multiplied with this 1, right? This AND gate. So that Q0 will come here. So Q0 or B1 will come. Okay. So if it is 0, then B1 directly will come. If it is not 0, then it will be changing. So because for example, if Q0 equal to 0, in this particular case Q0 equal to 0, at that time this Q0 0 will come here, because it is multiplying, and but this time B1 is equal to this B1 is equal to 1, but this particular line is 0, so we are having 0 here. So when you are taking product between B1 and 0, this thing will become 0, this line will become 0, and here we have Q0 or 0 will come. So then Q0 will come this side. Now your input is changed from B1 to Q0. That is the output of the first one. So shifting happening. Okay. So whatever the previous value of this first flip-flop is shifted into the second flip-flop. Similarly, for the other cases also, Q1 is going through this AND gate. Now this one is this is 1. So Q1 comes here, and this one is 0. So 0 will come here. 0 into B2 to B2. This line is 0. Q1 or 0. So this will become Q1, which means that your flip-flop 3 or 2 will be having input Q1, then that will be given output as same. So this Q1 is shifting to Q2. So shifting is happening after loading. So at that time it will be operating in the shift mode. The first one is load mode, the second one is shift mode, and in both way you can operate. So other things are same. So we have to shift continuously with the clock pulse. Okay, you have that clock pulse also here. Forgot that. We'll be having clock pulse also connected to all these flip-flops. Don't think that it is not there. So clock pulse is also there. You can draw that itself into yourself. You will be having that clock pulse like this. Each and every flip-flops in this case. Okay, so this is after this the shifting will happen. Okay, after loading, shifting will happen, and we have to take output through this particular flip-flop. This particular flip-flop, we have to take the output. Okay, and we'll be getting the output as we discussed earlier. You can also change the terms if you want Q3, Q2, Q1, Q0 like that also. That is also possible here. So here we have the output that has to be taken from this last flip-flop. That is the serial out. Okay. So here we need four clock pulses. We can directly give this inputs parallelly. As you can see, you can directly give parallelly, and but you have to take the output. In order to take the output, we need 4 cycles for uh, clock pulses. Okay, so these are the four different classification of the shift registers.